So, welcome to the fourth lecture of the course Basics of Fluorescence Spectroscopy. In the last class, we were discussing about the instrumentation of absorption spectrophotometer, the device which is used everywhere to measure the absorption spectra of the sample. And we have started with the single beam spectrophotometer as I was doing in this particular place. And as you remember, I said that my aim is to measure this I0 I, which is a function of lambda, that is it. And once I know the I0 by I can simply take this ratio I0 by I, and then I will take this log of that, which is a function of lambda, right. And with this, what I am going to get is A, obviously is a function of lambda. I will just simply plot A, the function of lambda versus lambda, I will get the absorption spectra. So, my aim is to determine that I0 and I for a particular value of lambda, particular value of light, particular color of light, right. So, I have started with this normal lamp, tungsten lamp in this case, and in this tungsten lamp, so this is obviously glowing, and as I mentioned last day, that the wavelength of light emitted by this tungsten lamp is really wide, starting from 450 to 1000. Now, if you use a general lamp, you can go to the UV region. If you use a deuterium lamp, you will get UV region also. So, depending on the choice of your wavelength, you will choose your own lamp. And now, obviously, you do not want all the lights to come and interact with the sample, because you want the wavelength dependence of the attenuation of the incident light I0 to I, which depends on the wavelength. Right. So, you use a device which is called the monochromator, which is nothing but the wavelength selector, and just as you have seen in that high school, that prism can divide the component of light, white light, to the spectrum. So, this device is simple like that. It is based on the gratings, and you can select the wavelength of light of your choice, right, using this monochromator. So, if you choose 500 nanometer light to come from this monochromator, only 500 nanometer light, obviously with some bandwidth, will come out of this device. If you want, it is not 500 but 600 nanometer, so 600 nanometer light will come out of this device with some bandwidth. Nevertheless, so with this light, right, what you got is the I0. That means you need to measure the intensity of this light, right, as desired. So, this is my sample position, right, this sample position. Sample position, and I incident this light of this particular lambda of your choice and pass through, right, and here is my detector, which detect the intensity of this light. Now, if I do not have any sample in this position, that means it is the blank one, then the signal intensity detected at this detector will be I0, right. So, I can get the value of I0 easily for this particular lambda, right. So, I0 for this particular lambda, let me name it as lambda 1. So, lambda 1, correct, and here is like this I0 for this lambda 1. Now, let me add sample right over here. So, now I add this sample over here. So, I have added sample in sample cell, right. Then the intensity, right, of this light of wavelength lambda 1 will no longer be I0, because some of the light will being absorbed by the system, right. So, let us that intensity is I for this lambda 1. So, simply you will get I0 and I. Once you will get I0 and I, you will be able to calculate A. right. So, just you take log I 0 by I, which is equal to A for this particular wavelength lambda 1. So, it looks very simple, looks very much fine, but there is some problem with such kind of setup. First of all, that lamp what I showed over here, this particular, let us say the tungsten filament lamp. So, the output of the lamp for this particular wavelength lambda 1, if I now may plot the output intensity of this lambda 1 from this tungsten filament lamp as a function of time, if it is like this. So, let us change the color, yes, here. So, the intensity versus time of the lamp output so the wavelength, obviously that wavelength I have already selected lambda 1, right. So, this is for lambda 1 wavelength, for wavelength lambda 1 I am going to plot the intensity versus time. This time is my real time, right. So, intensity if remain constant, then there is no problem with my previous setup. However, this is not like that. The real intensity profile along this time axis is something like this. The intensity starts from here, may increase, sometime decrease, like that way. Now, consider you are measuring I 0 at this time, right. You are measuring I 0 at this real time window, here you are measuring I 0 and you are measuring I when the lamp output intensity is little low, here you are measuring I in this real time window. That means, even the sample will not going to absorb a light of lambda 1, still here you will see that there is some absorbance or OD for this particular sample. That means, this is the error in the measurement, and this error in the measurement comes from the fluctuation of the intensity of the spectral lamp, right. So, we need to take care of that, otherwise the measurements will be erroneous and very much erroneous, right. So, people have developed the this particular setup is known as a single beam spectrophotometer. This is the very primitive setup for the spectrophotometric measurement, and so where shall I write here? Oh, I have written. So, single beam spectrophotometer, because there is only one beam. However, this particular problem of this spectrometer, what is the problem I said? That is the intensity actually depends, actually is a function of time, the intensity is not stable, right. So, although there is no change in the intensity supposed to be, but because of the intensity of the spectral lamp is changing. So, that could lead to generation of some absorbance of the sample itself. So, instead of this single beam spectrophotometer, what we can do? We can do this double beam spectrophotometer. So, in case of double beam spectrophotometer, so this is my double beam spectrophotometer. How I am going to solve this problem? I can easily solve this problem if I measure the I 0 and I simultaneously. So, whenever I am measuring I 0, I am measuring I, whenever I am measuring I am measuring I 0, right. If I can do that, then this fluctuation of this lamp intensity will no longer be a problem, right. So, simply what I will do, I'll do something like this. So, let us say this is my spectral lamp, right, and this emits light, and this light is being selected by the desired wavelength is being selected by this monochromator, right. You can set which lambda you want, right, and then I will do something where by which this light will be divided into two paths, right. So, I will use some optical element over here. This optical element is known as beam splitter, by which this light will be divided in two paths. Then I will use a mirror over here, and this beam splitter is such that, just consider this beam splitter is such that it will split the intensity 50-50. So, 50-50 beam splitter, half of the intensity will come in this direction, half of the intensity will come in the other direction. Now, you could have your sample cell over here and here nothing, right. You could have your sample over here and here nothing. The color of my sample was just for the consistency. Here is your sample, right, and here is nothing, right. So, if I now use a detector over here, this is one detector, this is another detector, then in this detector I am going to measure I, and at this detector I am going to measure I0, that is it. So, here I am going to measure I, and here I am going to measure I0, and now I can take log I0 by I, I will get the A. But here also there is some problem. The problem is that the sensitivity of these two detector cannot be exactly same. If they are not, then there will be a problem in the measurement of this I. Even if I said, and it is true, for example, that this light, the intensity of this light is divided in equally in these two different paths, this 50% this direction, another 50% the other direction, right. Still, because of these two detector, so take my word granted, no two detector in the world behaves ideally or exactly similar fashion, right. So, the performance of this detector will always be different than the performance of that detector, right. So, in this case probably then I should have I equal to I0, but you will never get this I equal to I0. That means, this is the problem of the detector, and if time permits and also if it is I found it required for this course, later on I will discuss little bit about this detector function, but right now let me just limited my discussion by saying just that the two detector response will be different, they cannot be equal to same in most of the cases. So, what I have to do, I have to somehow make a different design so that these two detector will be replaced by one detector, right. So, what you have seen for this one detector, this is only one detector, right. In this case what you have seen that there is a problem in the fluctuation of the lamp intensity, right, lamp intensity. So, now people have come up with varieties type of design. So, I need another page over here. So, the new design what we are going to have is something like this. now I have this lamp over here. Now I have wavelength selector. And from here, instead of that beam splitter, let us have a nice arrangement which looks something like this, and here one part of this is mirrored. So, this is mirror, right. Let me write over here, this part is mirror, this part is blank, right. So, nothing is there, open. So, this part is open and this part is opaque, complete opaque, black color. This part is completely opaque. So, when I set this optical device, one divided into 3 parts, one part is mirrored part, another part is open part, and another, the third part is the just opaque part, right. And this device is set in such a way that this is in the rotating condition. Some arrangement, some mechanical device has been used to make it rotate. And so, as you understand, whenever this incoming beam will fall on this transparent or open part, right. This is the transparent or open part, transparent or open part, it will pass through, that is it. And now, here I have my sample over here, sample, right, and then it will pass through the sample. However, whenever this incoming light from this monochromator will encounter the mirror part, because this is a mirror system, right, this is a circular device. So, it is rotating like this way. So, this is the incoming beam sometime. So, this is, let us say, opaque part, this is the mirror part, and this is the your transparent part. So, when it touch the mirror part, it will reflect it back, and when it touch the transparent part, it will pass through, right. So, when it touch the mirror part, let us say we have made the system in such a way that it will be reflected along this direction, and then I have another set of mirror over here, and it will pass through a place where sample is not present. That means, this is my sample and this is my reference, right, this is my reference. So, that means, this is my I0 and this is my I, right. So, this is my I0 and this is my I. Now, I have to combine these two somehow to get this I and I0 be detected with in the same detector, because there was a detector problem I said. So, now you use another mirror over here somehow. So, these are the mirror, let me write for you, MIRROR, this is also the mirror. So, you reflect this light, right, it is not good, okay. In this direction, right, and then you use another such a device where one part is opaque, another part is mirrored and another part is transparent, right, like this, and you set it the mutual rotation of these two mirror system, the circular mirror system, you synchronize in such a way that these two rotations are synchronized. in such a way that when this one is mirror for the first one, that means this light will be going to reflected like this, it will be transparent area for the second one, transparent for the second one, right. That means, when this light will be reflected in this direction, right, hope you will follow here, light will be reflected in this direction, then this light will pass through this transparent region, right, and will be detected by this detector, right, will be detected by this detector. So, you will be able to measure the intensity. Now, when this will be open or transparent area, for the first system, this will be the mirror area for the second one. So, mirror area for the second one. That means, when it is transparent, let me take another color over here to, when it is transparent, that means it will go through this system, it will pass through the sample and then will be reflected by this mirror and will be detected by this detector, right. So, for this in this case you will be able to measure this I. Here these two, these rotating mirror systems are rotated in high speed, so that in this graph, right, in this graph, if you are measuring I0, the measurement window of in real time, the measurement window of I0 and I are really small, and you are repeating this measurement many times. So, for example, earlier for the single beam spectrophotometer, this was, I said, no, this was your measuring window. Measuring window for I0 is this much, and I was like over here, right. But in this case, what you are going to do, you are going to measure I, this is I over here, you will measure I, then again you will measure I over here, again you will measure I over here, again you will measure I over here, and just next to it you are going to measure I0. So, for example, you are going to measure I0 at this position, another I0 at this position, another time I0 here, again I0 over here, and something like that. So, these are here, these are these all are I0, and this one, these all are I, right. So, I can measure this I and I0 in such a way that although there is some drifting in this lamp output, they will be compensated with each other, because I am measuring it many times over here. And if you notice over here, I am going to have another region which is this opaque region. So, this is also important part of this this opaque region, and with this we can actually minimize the error in the measurement of I and I0, because with this we can actually eliminate the dark count of the detector, So, let me stop over here for today, and in the next class we will going to discuss little bit of the application of this absorption spectroscopy, and then we will proceed to the fluorescence spectroscopic region. Thank you very much.